Hey everybody, this is the third and final video in a three-part series on category theory. Before watching this video, be sure to watch the previous videos which cover categories and functors. You can find links in the description. The goal of this video is to introduce the concept of a universal property and look at some examples. So let's get started. Categories and functors allow us to study universal properties. The best way to really learn about universal properties is to look at lots and lots of examples and see what they have in common. But we don't have time for lots of examples in this video, so instead I'll provide a general description and then present a few examples. A universal property characterizes an object in a category in an essentially unique way, in terms of its relation to other objects through arrows. This stands in contrast to characterizations that might refer to intrinsic details of an object, which are irrelevant from a category theoretic perspective. By doing this, a universal property abstracts away potentially complicated or messy details of a particular construction, leading to more elegant results. It also allows us to avoid repeating the same proofs over and over again in different categories. Once we know that an object in a category is universal, anything that follows from the universal property is known to be true of that object. Universal properties are analogous in some ways to interfaces in computer programming. For example, in the previous video we saw that the functor type class in Haskell specifies an interface, namely fmap, that functorial types must expose, but it doesn't specify any implementation details. Using a universal property in a proof is therefore like programming to the interface, in that you're only using things that are exposed by the interface, not any intrinsic details of the universal object. However, it's important to note that universal properties are stronger than most interfaces in programming because they determine objects essentially uniquely. The keyword here is essentially, and we won't dive into that in detail in this video, but in this analogy you can think of a universal property as defining a very strict interface. Like categories and functors, universal properties are everywhere. We now look at some examples. First, in the category of sets, consider the Cartesian product of two sets A and B, which consists of all ordered pairs of elements of A and B. There are many things you could say about this product. For example, you could talk about how the ordered pair is actually defined or implemented using sets. Maybe it's a Kuratowski pair or some variant. However, from a category theoretic perspective, there's only one thing that's really important about the product. The product allows us to freely translate between a pair of functions into A and B, and a single function into the product A times B, as we'll see in the next few slides. This property completely characterizes the product. From it, you can derive anything you need of the product without relying on intrinsic implementation details. Let's see how this property works. First, there are two projection functions, P1 and P2, from the product A times B into A and B respectively, which are defined in the obvious way. Second, for any function p into the product A times B, this diagram commutes. Here we form the composites of p with the projection functions p1 and p2 to obtain a pair of functions into A and B, making the diagram commute. Note in doing this we move from the inside of the triangle to the outside. Conversely, and more interestingly, for any pair of functions f and g from a set into A and B, there is a pair function p from the set into the product A times B, making this diagram commute. Here the function p must be defined in the obvious way. Note in doing this we move from the outside of the triangle to the inside. This all just means that the product, consisting of the set A times B and the pair of projection functions p1 and p2 from A times B into A and B, is universal in the sense that any pair of functions from a set into A and B can be obtained through this one in a unique way. This property can be used to define a product in an arbitrary category. In a category C, a product of two objects A and B is an object P and a pair of arrows P1 and P2 from P into A and B, such that for any pair of arrows F and G from an object X into A and B, there is a unique arrow P making this diagram commute. Let's look at another example of a product. What is the product of two propositions Q and R under logical implication? By definition of the product in the category of propositions under implication, it must be a proposition P implying both Q and R, such that any proposition S implying both Q and R also implies P. Therefore, P is just the conjunction Q and R. Actually, P need only be logically equivalent to the conjunction. If T is a tautology, then the conjunction P and T is also a product of Q and R, as you can verify. This example gives some sense of the uniqueness of the product. This example also shows that, from a category theoretic perspective, the Cartesian product of two sets and the logical conjunction of two propositions are the same sort of thing. They both satisfy all the same category theoretic properties. Recall from a prior video that for any category theoretic concept studied in a category C, we get a dual concept in the dual category C-op. This naturally leads us to the question, what is a product in C-op? To find out, we just reverse the arrows in the definition of a product in C. This leads us to the definition of a coproduct. In a category C, a coproduct of two objects A and B is an object C and a pair of arrows I1 and I2 from A and B into C, such that for any pair of arrows F and G from A and B into an object Y, there is a unique arrow C from C into Y, making this diagram commute. The concept of a coproduct is just as important as that of a product. As examples, it's instructive to work out what the coproduct of two sets is, and what the coproduct of two logical propositions is. I encourage you to do so. Rather than doing that in this video, we instead turn to another important example of a universal property which occurs in programming. In the Lambda calculus and functional programming languages more generally, functions of multiple variables can be implemented using functions of single variables which return functions. This technique is called currying, in honor of the mathematician Haskell Curry. By the way, the programming language Haskell is also named after him, but you really know you've made it when your name is in lowercase. As an example, the function which takes two numbers x and y as inputs and returns their sum x plus y as output can be implemented by the following lambda expression. Here we define an outer function which takes x as input and returns another inner function as output. That inner function takes y as input and returns the sum x plus y as output. Note that the inner function depends on the value of x, but doesn't take x as an input. The outer function returns a different inner function for each different value of x. To compute a sum like 2 plus 1 using this implementation, you would first pass 2 to the outer function, then pass 1 to the returned inner function to obtain the value 3. It turns out that this phenomenon can be described by a universal property. For types a and b, let b to the a denote the type of functions from a's to b's. This exponential notation is motivated by the fact from set theory that the number of functions from a set x to a set y is equal to the number of elements in y raised to the power of the number of elements in x. We can define an evaluation function epsilon from the product b to the a times a to b by this lambda expression. This function takes as input a pair z whose first component is a function from a's to b's and whose second component is a value of type a. It returns the result of applying the function to the value. That returned value has type b. Now, for any function f from a product x times a to b, thought of as a function of two variables, we can define the curried or transposed version f tilde from x to b to the a by this lambda expression. This is just like the definition of the curried sum function we saw on the previous slide, but for a general function f. Now the critical observation is that if we evaluate the curried function, we get the original function back. In diagram form, the situation looks like this. We have the evaluation function epsilon from b to the a times a to b. We have an arbitrary function f from x times a to b. And we have the transpose f tilde from x to b to the a, which makes the triangle commute. This all just means that the evaluation function epsilon is universal as a function from a product with a into b. Any function from a product with a into b can be obtained through epsilon in a unique way by currying. The object b to the a, together with epsilon, is called an exponential. Like a product, an exponential can be defined in an arbitrary category. A category with all finite products and exponentials is called a Cartesian closed category. As an example, we've just seen that the category of types and functions in the lambda calculus is Cartesian closed. More generally, these categories provide semantic models or interpretations of the lambda calculus. For any specific system of types and terms in the lambda calculus and equations relating them, there is a Cartesian closed category modeling the calculus. And conversely, every Cartesian closed category is the model of some calculus. So once again, we have a very close connection between category theory on the one hand and functional programming on the other. That concludes this video series on category theory. Here are the references I used in preparing the series. I highly recommend you check them out if you want to learn more. Thanks for watching.